Good day everyone. So for this video, I will be teaching you conservation of momentum. And to start with, take note that conservation of momentum happens only when a system is free from external forces such as friction. And these systems are called isolated system. For example, in this case, we just assume that this scenario has an isolated system, meaning there is no external forces or there are no external forces acting on these two objects, or there is no friction acting on these two vehicles. And to see whether the momentum is conserved, let us first check the total momentum of these two vehicles before they collided with each other. And to identify that, we have to know first the momentum of each vehicle. So, the momentum of the first vehicle before the collision is 20,000 kilograms meters per second. So, take note of that. And then, for the momentum of the second vehicle before the collision, that is negative 60,000 kilograms meters per second. So, you take note of these two variables, and to get the total momentum of these vehicles before they collided with each other, obviously we have to just sum them up. And as we add them to each other, we'll have this sum, negative 40,000 kilograms meters per second. Now, let's check the total momentum after the collision. So, for the total momentum before the collision, we have to get first the momentum of the first vehicle after it collides with the second vehicle. So, after the collision, the first vehicle becomes negative 40,000 kilograms meters per second in terms of its momentum. And then, for the second vehicle, its momentum after the collision becomes 0. So, to sum them up, we'll have negative 40,000 kilograms meters per second. And with this in mind, what can we infer about this computation or situation? So obviously, we can infer that the total momentum before and after the collision is conserved or equal. So after knowing the context of how conservation of momentum works, let us express this mathematically in full details. So earlier we mentioned that the total momentum before the collision is equal to the total momentum after the collision. And that one can be expressed by this equation. So for P sub I, it pertains to the total momentum before the collision. On the other hand, P sub F pertains to the total momentum after the collision. And obviously, for each variable, it has subcomponents. Similar to what we did earlier, we identify the momentum of each vehicle before and after the collision. So, for P sub 1, the subcomponents will be the momentum of the first car before the collision. So, P sub 1 represents the momentum of this first vehicle before the collision. So, that is the 20,000 kilograms meters per second in this case. And then for P sub 2, that is the momentum of this second vehicle before it collides with this car. And in this GIF, its amount is negative 60,000 kilograms meters per second. And then for P sub F, the subcomponents will be the momentum of each vehicle after the collision. So we'll just have a little change in terms of the symbol. So we will place this as an indicator that the momentum changes. Okay? So, P sub 1 change, that is the momentum of the first car after the collision. So, that is negative 40,000 kilograms meters per second. So, for the P sub 2 change, that is the momentum of the second vehicle after the collision, that is 0. But we're not yet done. Since each momentum has subcomponents as well. Just like what we were discussing in our previous lesson, we argued that momentum depends on mass and velocity of an object. So, for this scenario, the P sub 1 or the momentum of the first vehicle before the collision is the mass of the first vehicle before the collision and its velocity before the collision. And we can represent that by these variables m sub 1 times v sub 1, mass of the first car and the velocity of the first car before the collision. And then, for P sub 2, so that is the mass of the second vehicle and the velocity of the second vehicle before the collision. So, here, we can see the mass and velocity of the second vehicle before the collision. And then, for the other side, for P sub 1 change, so we are referring to the mass of the first vehicle and its velocity after the collision. So initially, the velocity of the first car is 20 meters per second and then it becomes negative 40. So that is the V sub 1 change. And then for P sub 2 change, its subcomponents will be the mass of the second car, okay, after the collision, and then the velocity of the second car after the collision. So, initially, the velocity of the first car, the second car rather, is negative 20, then eventually after the collision, it becomes 0. So, if you will be looking at this variables, what changes only or what change only are the velocities of each vehicle. Okay? If you can still recall that if an object experiences an impulse, what changes only is the velocity. The mass is constant. Okay? So that explains why in this scenario, the variables that change only are the velocities of each vehicle or each object. So, my challenge for you is for you to replace these variables by the values provided in the GIF. Okay? So, pause this video and try to write your answer or write your answer, not try, but you have to really write in your notebook the answer or your answer for this challenge. Okay? So let's see if your answer is correct. Alright, so here, mass of the first vehicle, that is 1,000 kilograms, and it does not change even after the collision, it's still 1,000 kilograms. Okay? And then, the velocity of the first vehicle after the collision is 20 meters per second. Okay? You can see it here in this table. And then plus the M2, which is the mass of the second vehicle, 3,000 kilograms. Okay? Here, you can see the mass of the second vehicle, 3,000. And after the collision, it does not change. It's still 3,000 kilograms. You can see it here in this GIF. Okay. Then, after the collision, the velocity, before the collision, the velocity of the track is negative 20 meters per second. Okay. Then equals the mass of the first vehicle. Then, the velocity of the first object after the collision is negative 40 meters per second. So, from 20, it becomes negative 40 meters per second. then plus 3,000 kilograms. Again, the mass of the second car does not change, or the second vehicle, okay, it does not change. What changes only is the velocity. So from negative 20, okay, meters per second, it becomes 0. It stops. Okay? So hopefully, you get this part. But for the next video, what if we do not know um, one variable? Okay? Because not all the time we know the variables or the values of the variables. They are not provided. So for example, what if we do not know the velocity of the second car or second object after the collision? So we have to derive a formula. And that will be the focus of the second video. See you.